Okay, this is the MHD Experiment by Hugh Mayo.
Aaron Levon.
And Tommy Ostrom.
So what is MHD? MHD stands for magnetohydrodynamics. So if you kind of break that word apart, you get magneto for magnets and hydrodynamics for moving water. Overall, it is the use of electric and magnetic fields to manipulate electrically conductive fluids. And we'll kind of get into more detail about that later.
So to set this experiment up, we created a small magnetohydrodynamic pump. The channel is comprised of 2 electrodes dipped in a pan of salt water. The salt adds ions to the water, making it an electrolytic solution. And here you can see the copper is the electrodes, and we used alligator clips to move the electricity through the water. And there's pepper in the water so we can see the water moving. When we attach the power source to the electrodes with the alligator clips, the solution acts like a wire would, and the circuit is completed.
So this is kind of the general idea. So since we have electricity flowing between the 2 electrodes, we have a lateral electric field. So if you just imagine a vector going between those 2 electrodes sideways. And next we put a magnet below the channel, creating a vertical magnetic field. So you can't see it right now because it's obscured by the bubbles, but but there's a small magnet under the pan, and that's creating a magnetic field going upwards. You can see that in more detail a little bit in this picture, a little bit more conceptually. It's a sideways version of our experiment, but you can see that there's the electric source, and it's showing that there's a circuit between the electrodes on the top and bottom. We have ours on the sides, and then you've got the north and south poles of the magnet. So the electrodes are creating that electric field going down, and the magnets are creating a magnetic field going sideways. So when the electric vector and the magnetic field vector come together, they make a third vector. This process is known as a cross product. This third vector is called the Lorentz force, and it pushes the water through the channel. So you can kind of see those 2 electric and magnetic vectors coming together. And when they do that, you can see that third arrow pointing outwards towards you, and that's the force of the water moving. The bubbles occur. Wait, I think that's you.
So the bubbles occur because of the electrically stimulated chemical reactions, and we can solve this problem by using a different kind of current that we used in our next experiment.
Here's the video. Before we get to that, here's the video of the first experiment. There you can see the bubbles moving, showing the flow of the water. And those bubbles are mainly hydrogen gas, and I think maybe possibly a little bit of chlorine gas from the NaCl, the sodium chloride. So more on the next experiment we did to solve that bubble problem.
So as I said earlier, to remove the bubbles, we used a different type of current called alternate current. So direct current creates an electric current in one direction, as you can see in the straight line, whereas alternate current quickly switches the direction of the current, as you can see in the sine wave. This is the setup of our second experiment, and he will explain a little bit more about the setup.
So as you can see, we've got the same electrodes, alligator clips, and solution. The only difference is that we're running alternating current through it, so the direction of the current is switching at a high frequency. And when we're switching the direction of the electric field, so we're switching that arrow that's going down back and forth a lot, we need to switch the magnetic field in time with it, so we make sure we get that same arrow coming towards us. So this big coil is actually an electromagnet, And the electromagnet can be used when you put it in a circuit with the electrodes. It switches the electric and magnetic fields in time. So when we do this, the ions get a little confused, and we get they kind of can't decide what state they want to be in. So we get flow without the bubbles occurring. It kind of stops those chemical reactions. So no, we're now switching the direction of the electric field. So again, we had to put them in series so we get everything in time. And here's what we did.
Oh yeah, can't really film that though.
So it's kind of close right there, but you might be able to see a little bit of pepper flakes moving.
Yep.
There, and there.
But you got the setup, right?
The setup. You want me to take a picture?
All right. So here's examples of the use in industry.
So you can see here by the diagram, you can see the phenomenon that Hugh explained earlier with the two vectors and the third one forming the flow. And this seawater vessel uses the same phenomenon in its propulsion unit so that it can propel itself at sea. And also the sun uses the same MHD phenomenon, and instead of salt water, it is made of plasma.
So obviously the sun isn't quite pumping anything, but it's just to show that there's the electric fields and the magnetic fields are both the processes is occurring in the sun, except the difference, the reason why it works so well is that plasmas are made of really, really hot ions, and what you have in a salt water or an electrolytic solution is similar ions. Of course, plasma is much hotter, so that's MHD for you.